Okay. Hello, guys. This will be your lecture 7. Today we're talking about limit and continuity, which is section 14.2. And this will be the actual section that we start doing calculus. So make sure you understand what we're doing now. Right. So a brief introduction. I will split this section into three portions. The first one is a brief review on the one-dimensional limit and continuity, which is what we will cover in this video. In the second portion, I will introduce you the limit and continuity in higher dimension, in our case, the 2D and 3D dimension. And the last video will be a supplement. It'll be the proof of what we had covered in the first two videos. And that will not be necessary for you guys to comprehend. It is just for completeness. So if you guys are interested in the theoretical aspect of those theorems, those propositions, then feel free to check out the proof in the third video. But as for the conceptual ideas and actual examples that will appear in your exams and quizzes, then I would say that the first two videos will be sufficient. Right, now let's start with the review. So, first let's talk about as I mentioned, let's talk about the one-dimensional definition of limit. So basically, actually, let me first mention the definition first, and I will uh, briefly explain it conceptually. So, given a function f, obviously in this case, f is a single variable function. So basically, f sends some number to some number. Okay, those are numbers, not vectors. So we say the limit of f at the point x equals to a, so that is some point a, is L, and we denote that phrase by this notation, limit of x at a of this function f is L if the following is satisfied. So given arbitrary epsilon larger than 0, so epsilon is another Greek notation. So given an arbitrary positive number epsilon, there always exists a delta that has another Greek number, a Greek letter, so that the following happens. Whenever x is close to a, meaning that x minus a, the distance, is less than delta, then f of x minus L is less than epsilon. So there's a few nuances here. Let me go through this step by step. So this is a rigorous definition of limit, but basically what it is saying is that whenever x is close to a, so whenever delta is small, that means that f of x is close to L. So that is when epsilon is small. So what this definition said is that the definition of the limit of f at a being L is equivalent of saying that f approaches L whenever x approaches a. Okay, that's the basic definition. But in order to make a more quantifiable definition, to make sense of what the limit is, we present this kind of abstract definition, right? All right. Another small thing to notice here is that I add a condition here, which is 0 less, strictly less than. So basically that just means that x is not a, right? Because the absolute value is always non-negative. So why do I add that condition? That means that technically speaking, we don't have to define f at the point a to get a limit. So what I'm saying is that all of this concepts only depends on the behavior near the point A instead of A itself. So by saying the limit of f at A is L, we're simply saying that for any point close to A, the value looks like L. But we don't really care about the point A. So whether f of A is defined or not, it is safe to say the limit of f at A is some number L. Okay, that is what I'm saying here. So let me put it in a graph. So you see that this red curve is, actually I didn't mention here, it should be y equals to f of x. So this is the graph of this one-dimensional function. And this is axis for a. and that is y equals to L. So, according to my definition, I'm saying that whenever threshold, which is a small interval, oh, actually, sorry, I didn't read this correctly. I don't know why. Let me correct that. Wait a second. Right. So I'm saying that. Uh, Let me draw the picture more perfectly. Okay. Right. So I'm saying that whatever small interval you drew between L, so in this case, f of x minus L less than epsilon. So we drew a small interval within the value L. You can always find a even further smaller interval around x, so that the value within this interval lies between L plus epsilon and L minus epsilon. And you can see in my graph that if you, however small you shrink these two guys, you can still get a smaller interval which satisfies the definition, right? So basically, we're saying that every value of f near A looks like L. Okay, so this is what it graphically means. And I hope you guys under that definition. And under that definition, we define additionally the continuity. So continuity has to do about what I just mentioned about the definition of f. Supposedly, the limit of f at the point A is the same as the value of f of A, then we say that f is continuous. So basically, a limit exists already tells you that the function behaves well near the point. So it behaves well in the sense that locally it looks like the same value. And additionally, if we plug that value in to define the function, then that function will be continuous. And basically, continuous coincide with our usual intuition, which is that you can draw the line without having to raise your pen, sorry. So here's a quick example. In this example, you see that this function is defined like that, and a solid point means the definition of f of a. So this guy is f of a, and this point is nothing, it's empty. And for the function, for the value, sorry, for the input larger than a, this is the function f of x. So we note that the function limit does not exist at a. That is because that when you go in this direction, you get something higher. When you go in this direction, you get something lower, right? So according to our definition, the epsilon delta definition, if you fix L to be, say, this value, you can create a small threshold, this light purple threshold, so that actually the value near to A does not fall into this threshold, right? Similarly, if you want to say that the limit is this number, then if I create this purple threshold, you can see that the point that is lying to the right on A does not fall into this threshold, right? It actually falls here. So that is why this limit does not exist. And in particular, whenever a limit does not exist, obviously it is not continuous because the existence of limit is a precondition of having a continuity. And as for this case, this actually has a limit because you see that the local behavior looks very much alike near A. It actually has a limit here. However, if we define f of A to be this point, this value, then this is not continuous because although it has a limit, but a limit is not the same as the function value. So this is not a continuous function. So there is two possible scenarios of discontinuity. One case is like this: whenever the limit is not does not exist, this is called jump discontinuity. And another case is like this, where a limit does exist, but it does not coincide with the function value. This is called a removable discontinuity. The name is not important, just the scenarios. So we understand that there's two different types of discontinuity. Okay. So in order to treat that definition more precisely, we introduce further the right and left limit, which is defined quite similar to the limit. So we define a right limit of a function f at a, again, denoted by limit of x tends to a plus. So we're approaching a from the right-hand side. So we denote by a plus. Somebody use this notation where x goes down to a because we're approaching x from the right. It's all the same, and I prefer this guy, so I will use this for the rest of the section. So the definition of Blitz notation is something like this, which is a lot similar to what we have done. So given an arbitrary epsilon, so epsilon is the threshold between f and L, there always exists a delta so that this happens. So whenever x is to the right of a, and it's within this small interval, a to a plus delta, so x is within this small interval, then f of x and L are close. So let me phrase this in English again. It is saying that whenever x is to the right of a, and it is close to a, then f of x is close to L. Okay? So similarly, for the limit of f, for the left limit of f at a, is saying that whenever x is to the right of a, and x is close to a, then f of x is close to L. Right? So for instance, the left limit of this function at a is this guy. And the right limit of this function at a is this guy. So you can sort of anticipate what we're going to do now. Actually, limit is just a combination of right and left limit. So we know actually by definition that the limit of function f at the point A exists if both the left limit and the right limit exist and they're the same. So let's go back to the previous example. This is the case where you have a left limit, you have a right limit, but they don't coincide. So there's no limit. And this is the case where you have a left limit and you have a right limit, and they're the same. So it does have a limit. Okay. So in addition, we have this criteria for continuity is that whenever the function value is defined, and also that the limit exists, and the limit is equal to the function value, then we say it is continuous. So both of these are quite direct follow from definition. And the reason that we introduce this left-right limit concept is that it is a more understandable way to evaluate limit because it is more practical to analyze the right behavior and the left behavior to see whether it coincides at the same point or not. So we have done this in calculus 1, I guess. So every function that you're familiar with, polynomial, trigonometric, exponential, or arithmetic function, are actually continuous in the domain. So obviously it cannot be continuous on something that you're not defined. And for example, tangent x is continuous on minus pi over 2 to pi over 2. And it is actually not defined at pi over 2, right? So we cannot speak of the continuity there. But it's always continuous on each of its interval. And similarly, say logarithm of x, ln x, is continuous on the positive axis because you cannot define ln of minus 2, right? So it is natural to speak of the continuity on their respective domain. Okay. And now having that definition, let's show the power of that definition. So I just want to mention here that, however, since we're dealing with this precise abstract definition of limit, it is not crucial for you to know how to operate that kind of definition, but it is crucial for you to understand the concept of definition. Basically, it's saying that whenever f approaches L at A, then we say that the limit of f at A is L. Okay, that's the idea. And to operate it, it will take more time and take more practice, but I will encourage you guys to try to follow what we're going to do in the rest of the semester. So I will always provide a complete proof in the way of the epsilon delta language. It is not necessary for a course, but I will guess that it will help you comprehend the concept. So let's start. This will be our first epsilon delta proof. So say we define this function. This is a piecewise defined function. So when x is strictly less than 1, we define it to be 3x, a linear function. Whenever it is larger or equal to 1, we define it to be x plus 2. It is also a linear function. So it is actually defined like this, 3x and then x plus 2. We want to show that f is actually continuous at 1. So let us prove this. It is almost direct from the graph, and however, we cannot believe what we see. The point is that we have to have definition for everything and actually prove that definition for everything. So in this case, what we want to show is that f is continuous at x equals to 1. So what do we want to show? We want to show precisely, first of all, f is defined at 1, which is okay because f of x is defined at 1. You can evaluate to be 3, right? Secondly, we have to show that the limit exists and it is actually 3. So this is what we need to show. We need to show that the left limit and right limit exist and they are both 3. Okay? So then let's do this. So as for the left limit, what we want to show precisely is whenever x is close to 1 from the left, then f of x is close to 3. Okay, that's our proof. So let us choose an arbitrary epsilon. The epsilon should be arbitrary. We can choose any kind of number. You can choose 100, you can choose 10, you can choose 10 to the minus 1,000. Any number should be satisfied if you want to find a limit, because we're approaching the point 1 close and close and close. Closer and closer and closer. So in this case, suppose I pick delta to be epsilon over 3. So for example, if epsilon is like 1 over 10, then delta is 1 over 30. So you see that the distance between f of x and 3, since x is on the left-hand side, so we use this definition. So you have 3x minus 3, which is equal to 3 times the absolute value of x minus 1. However, we set up so that the x is of distance epsilon divided by 3 to 1, right? So this is less than a third of epsilon, making this less than epsilon. So we see that by setting up this kind of x, which is on the left to the left of x, and is within the distance of delta to 1, then the distance between f and 3 is always within epsilon. So that basically shows that the left limit of the function f at the point 1 is 3. Now we can do a similar operation on the right-hand side. So you see that, again, we fix an arbitrary epsilon. Epsilon is any number, any positive number. In this case, we pick delta equals epsilon. Actually, anything smaller will be sufficient. But let us see why this is the case. Since we're now on the right-hand side of 1, so we're applying this definition, right? So f of x minus 3 is now x plus 2 minus 3, which is simply x minus 1. However, we have already fixed our x to be within delta distance of 1. So this is less than epsilon, since delta is just epsilon. So both of this case shows that whenever I choose whenever I'm given an epsilon, I can always choose a corresponding delta, so that the distance within f and 3 is less than epsilon whenever the distance between x and 1 is within delta. So that sounds familiar, right? Basically, that is saying that the limit of f at 1 is 3. And 3 actually coincides with our function value f of 1. So we show that the limit of f at the point 1 is actually f of 1, meaning that it is continuous at the point 1. I know this might sound really abstract and kind of unnecessary, since this thing is quite plainly obvious to be continuous, but there will be some really strange function which we don't understand whether it is continuous or not. And this kind of abstract and quantifiable definition is for those functions. So this is just a plain example to show the power of that definition, so that we can actually prove things without having an intuition about it. I hope that makes sense. Okay, so after the introduction of limits, let us sort of state the behavior of that limit. So this is the arithmetic of limit. Whenever f have a limit at a, and it is L, whenever g have a limit at a, it is M, then we have the following propositions. So first of all, the limit of the limit of f plus g at a will be L plus M. And the same thing holds for subtraction, multiplication, and division. The division has an additional condition, which is that the limit of g at a cannot be 0. And that is quite obvious why that is the case, because we cannot divide things by 0, right? In the case where both L and M are 0, it's a different story. It is like L'Hopital's rule or some more delicate treatment of limit, which we will not discuss today. But those are the arithmetic of limit. So it is very nice in the sense that it actually operates the same, just like the usual algebra. So what we're saying is that, say, addition and the limit are exchangeable. You can do the addition first and take limit, or you can take the limit first and then do addition. And the same holds for subtraction, multiplication, and division. So based on those properties, we know that we have a additional property about continuity. So suppose f and g are continuous at the point A, that means that L in this case is just f of A, and M in this case is just g of A. So obviously that means that the limit of f plus g at A is simply f of A plus g of A, which is the function value of f plus g at A. So continuous function is actually a nice space with respect to addition, subtraction, division, and multiplication. So that means that f plus g, f minus g, fg are all continuous at x equal to a, and also this is also continuous whenever again the function value of g at a is non-zero. Right. So that's all. I guess you guys have learned that back in calculus 1. So another nice thing about limit is that we have this three-squeeze theorem. It is in general not always simple to find a limit, which we will demonstrate just now. And there's a nice theorem that treats that kind of scenario. So whenever you have a function, f, we're interested in the limit at a, and you have a say layer of functions, so that g is less than f is less than h for a small neighborhood around a. So this might sound redundant, but I'm just stating this fact because you can see in my picture that g can actually be larger than f, and h can actually be lower than f someday. But what we actually care about is the value near a. So we see that actually near a, we always have h larger than f larger than g. That's what we care about. Okay, so suppose that both h and g have the limit L, then obviously f is squeezed between these values, right? So f can only have limit L. So that's the squeeze theorem. And it is practically useful whenever the functions g and h are simple and you can calculate their limit directly, whereas f might not be that simple. Okay, now let's do a very classical example, which I guess you guys have done in calculus 1, and I'll just demonstrate this here to show the power of squeeze theorem. So this is a function sine theta over theta, and we want to understand the limit behavior of this function near 0. So you can see that obviously this function is not defined as 0 because you cannot divide 0 by 0. That is nonsense. So again, I mentioned in the first page that technically we don't need to define the function at a point if we're calculating the limit at that point. We only care about the local behavior of the function at that point. Okay, so a nice trick about this kind of limit is this diagram here. So you see that I drew a unit circle, actually a fourth of a unit circle, where each length is 1, the radius is 1. So if I label the origin as O, this point is B, this point is D, this point is C, and this point is A, with the angle theta, you see that by definition, this guy is cosine theta, right? And this guy is sine theta, whereas this guy is tan theta. So the inequality that we will use is that the area of OBD triangle is less or equal to the sector of OAB is less or equal to the triangle OAC. And now we calculate this areas using theta. So for triangle OBD, it has base cosine theta and height sine theta. So it is half of base times height. And for a sector, recall that the sector formula is half times r squared times the angle theta. So it is half times 1 squared times theta. Last, the triangle here has the area of 1 times tan theta divided by 2, whereas tangent is defined to be sine over cosine, right? So how does this yield the inequality that we want? We see that if I divide, let's use this guy first. So first of all, I can divide the half out of the inequality, right? Secondly, cosine theta sine theta less than theta can be interpreted as sine theta divided by theta is less or equal to cosine theta, right? So similarly, theta less than sine over cosine can be interpreted as cosine less than sine theta over theta. So technically, this kind of algebra depends on when theta is positive. So that means actually put a plus sign here. But you can prove the negative sign similarly. Okay. Um. Yeah. So we have our nice inequality. Whereas since cosine is continuous at 0, so the limit of cosine at 0 can be evaluated by the direct substitution rule. I think that's the name. So you can plot cosine 0, which is 1. Similarly, the right-hand side gives you 1 over 1, which is still 1. So by Squeeze theorem, we know that the limit of this guy and this guy is 1. So this guy is shrink within that threshold, give you 1. The limit of sine theta over theta is 1. So again, technically, I'm proving the positive part, so let me put a plus here. And I encourage you to try the negative approach. It is the same thing, actually. Right. So for our last example, oh, sorry, I have a remark to make. So this y equals f of x is a function I just mentioned, the sine x over x. So as we see that this is not defined for 0, right? But we can naturally extend it to 0 in a sense that if I introduce the notation of f of 0 to be 1, then it will be continuous because we know that the limit at the point is 1, right? So this is a way to define a value that is not defined for a particular function. So if we know that the function behaves nicely near a point in which the point is not defined, then we can simply define the value for that function at the point to be a limit to make sure that it is continuous, right? So that is why it is called removable discontinuity. We can replace the function value to make it continuous. The last proposition I will introduce in this first portion of the video is that limit and continuity also behave well under composition. So in this case, I state that when x approaches a, f approaches z, and when y approaches c, g approaches L, then we have a nice formula for composition. So let us recall this notation, G circle F. So G circle F of x is a new function defined by G of F of x. Okay, it is called composition of G and F, which is quite crucial in our practical example afterwards. So we're stating that this function also have a limit at a, and it is defined to be L. So naturally, it is quite natural since in the case where x approaches a, this guy approaches c, right? So this guy approaches c. However, we know that whenever the argument of g approaches c, it approaches L. So eventually this guy will approach L. So that's basically how this works. And so based on the first item here, we know that if f is continuous at a particular point A, and g is continuous on the value of that point f of A, then g circle f will be continuous at A. And this is also direct from the first proposition. See that we're saying that f is continuous at A, right? Whereas g is continuous at f of A, so g of y is g of f of A. So combining this with our previous proposition, we know that g of f of x is simply g of f of A, right? Which shows that the continuity of g circle f at the point A. So how does that help us? It helps us in the sense that we actually extend our class of continuous function by a large amount. So for example, we know that polynomial trigonometric logos is a continuous function, right? But we now know that you can compose any function to make even more continuous function. So for example, this is polynomial, continuous. This is trigonometric function, continuous in its domain in particular. This is constant function, which is also continuous. Then, since tangent function is continuous at its domain, so this whole guy here is continuous by our previous proposition, right? A continuous function composed with another continuous function is still continuous. So you see that, as I mentioned here, if we set g to be tangent, f to be the argument, then since f is continuous at the point 0, and y is continuous at the point pi, which is the value of this guy at 0, then this whole thing is continuous as zero. So you can do direct substitution. The limit of g circle f is simply g circle f0, which is tangent pi, which is zero. So that is how convolution, which is the fifth operation that we have done with functions, help us extend the class of continuous function. Right. Um, so as I mentioned, things like this, the proposition of these propositions, these theorems, the proposition will all be given a proof in the third portion of the video. And we will encounter almost the same thing in the high-dimensional limit and continuity, which we will be doing things more delicately. And we will soon see why in the next video. But anyway, for this first video, we have recovered the definition of limit of a single variable function, the definition of continuity of a single variable function, which is that the limit coincides with the function value. And we have see a small analysis on limit, which is we break it down into the left and right limit. And if those limits exist and they are the same, then we have a function which has a limit at the point. And we demonstrate some example using applying the definition of limit to show that the limit exists instead of proving by intuition. And then we see some arithmetic of limit, stating that the limit is behave nicely under addition, multiplication, subtraction, division, and also the convolution. Whereas those properties are also satisfied under continuity. So two continuous function gives you a continuous function whenever you're doing addition, subtraction, division, multiplication, and convolution. Lastly, we have another nice theorem which is called squeeze theorem, which is a way to compute the limit via constructing two simple functions around the target function. And if those simple function has a identical limit at a point, then we can compute the limit of that perhaps complicated function at the point A. Okay, I think that's all. I will see you guys in the next video to introduce the limit of our multivariable function, which is a lot similar to the single variable function, but needs a bit more treatment. So see you guys.